Hello everyone, now we are going to solve the next question of GATE 2011. This is simple questions, okay? A disk of mass m is attached to a spring of stiffness k as shown in figure. The disk rolls without slipping on a horizontal surface. The natural frequency of vibration of the system is. That means the system is given, we have to calculate the natural frequency, but as you can see in the options there is a multiplication of 1 upon 2 pi. That means it is saying that it wants to say that you have to calculate the frequency in hertz, because is in hertz we know that this is the omega n upon 2 pi. That means you have to see multiplication of 1 by 2 pi. Okay, so that's why we have to calculate the frequency in hertz. So this is the, generally then don't mention the find out the frequency in hertz, but you have to check through options what it means. Okay, so here you can see that we have to calculate the frequency in hertz. So these questions we can solve either by torque method, that generally we apply in every questions because it is easy to write down the equations. So but here we can also solve the questions using energy method. So both the methods I am going to tell you here. So first we will solve this question by energy method. When you apply the energy method, we know that in case of natural vibrations, we don't consider kinetic frictions. That means the kinetic friction is equal to 0. That means there is no energy loss. If there is no energy losses, that means energy remain constant. If energy remain constant, that means dE upon dt is equal to 0. So we have to find out the energy and then differentiate it with respect to t and put it equal to 0. That would be our equations of vibrations. Okay, so what is the energy equations? Basically E is equal to, you can see there is a disk. Okay, this disk is going to be rolled, as well as it is having some velocity, linear velocity as well as angular velocity. So there is a potential energy of the spring also. So that means there are three types of energy. One is half mv square, plus second is half I omega square, that is the rotational kinetic energy of the disk, and the third is half kx square, that is the potential energy of the spring. Now dE upon dt equal to 0. If dE upon dt equal to 0, that means dE upon dt is equal to, you can see that half mv square, that means half m, because mass is constant, 2v dv upon dt, plus half I omega square, that means you can write omega is equal to v by r. We all know that omega is equal to v upon r. Okay, so you can replace omega as v by r. So that means half I upon r square and v square. V square means 2v dv upon dt. Okay, 2v dv upon dt, plus half kx square, that means half k 2x dx upon dt, dx upon dt. So that means this would be cancel out and this would be cancel out and this would be cancelled out. You can see dv upon dt is acceleration, and acceleration is denoted as x double dot. So that is mv x double dot. We all know that I is the moment of inertia, and moment of inertia of for the disk is mr square by 2. Mr square by 2. Okay, so that would be plus I means mr square by 2. So mr square by 2 over half mr square, and there will be a, in the denominator r square, there will be r square in the denominator. That means both will be cancelled out to each other. That means if you write mr square upon r square is there, so both will be cancelled out to each other. Okay, so I'm just writing here directly. So that is mv dv upon dt is acceleration, that means x double dot, plus that is kx, and we know that dx upon dt is velocity, so that is v, and we have to put it equal to 0. Equal to 0, you can take common v. Okay, so the remaining equations become, this is m by 2 and this is m, that would be 3m by 2. x double dot plus kx is equal to 0. When you rearrange these equations, it would become x double dot plus 2k upon 3m x is equal to 0. And when you compare these equations with the equation of natural vibrations, so you can see that this would omega n square, this term is omega n square, that means 2k upon 3m. From here you can get the value of omega n, under root of 2k upon 3m. But here in the options you can see there will be a frequency in hertz, so you have to multiply with 1 upon 2 pi. So frequency in hertz, that is 1 upon 2 pi omega n, that means under root of 2k upon 3m. Okay, so option C is correct answer. You can see I have not seen what is the options given, but we are doing the correct procedure, that means you will get the correct answer. So option C would be the correct answer for this question. You can see here. So this type of questions can be solved either by energy method or the torque method, but this can be a lengthy process if you apply the energy method. If you apply the torque method, it is easy because in the torque method directly you can write the equations. You need not to differentiate anything because this may be a time consuming process. So I'm telling you how to solve it using torque method. So if you apply the torque method, you can see that this is the disk, okay, and this is the point of contact C. If I rotate this disk through a small angular displacement like that, so this new position of the center would be here. Suppose this is a small displacement I have given theta. So if theta is in that direction, if theta is in that direction, I theta double dot would be, this is the inertial torque in the opposite direction of motion, and there will be a torque just because of spring force, that would be k. This is the displacement of spring, okay, this would be the, so that is k theta r multiplied torque we are taking about c, so that is r. So you can see there are two terms, so we just have to put here I theta double dot plus k r square theta is equal to 0. Okay, basically we are going to apply the D'Alembert principle. Okay, so here when you rearrange this, theta double dot plus k r square upon I theta is equal to 0. So you can see that this term is basically representing the omega n square, that means omega n is equal to under root of k r square, if r is the radius of the disk, upon I. But here I will not be mr square by 2 because we are taking the torque about point of contact C. So we have to consider the moment of inertia about point C. Okay, so that is mr square by 2. This is the moment of inertia about center of gravity plus mx square. X is the distance between the point about which you are going to consider torque and the center. So that is r. So you can see there will be a 3 by 2 mr square. So when you put this value here, so you will get 2k upon 3m omega n. So you can find out the frequency in hertz, 1 upon 2 pi under root of 2k upon 3m. You can see that this is a simple procedure and there is no time consuming in case of torque method. So that's why we generally use torque method in the examinations, because it takes less time to solve the questions. We just need to write down the equations, okay, but just by giving the small angular displacement to the system. Okay, so I hope you will understand the procedure.